had too much of a hassle where we've done one where you've got, if I look at this one, 4x squared minus 24x. If I do that, if you do 4x squared minus 24x, what's the first rule of factoring? GCF. We always look for a GCF. So in this case here, I'm going to write this down here. So your GCF is a 4x, and you're left with x minus 6. Is there anything left to do? No. Did this say equals 0? No. So you don't have to solve for zeros. Okay, that's the only difference. Now, if I look at one where, if I look at this one, x squared plus 10x plus 25 equals 0, what is that asking me to find? The zeros, right. Solve for x. What does x have to equal? Well, what times what's 25 you add together to get 10? 5 and 5. So if I factored this one, you move this guy out of the way here. If I factor this one, I'm going to get x plus 5, x plus 5 is 0. Now this gives me a what we call a duplicated 0. Where? At negative 5. Now remember what happens when you have a duplicated 0. What happens with the graph? Yeah, it just changes direction at that spot. It touches the graph at one value. It works the exact same way when we get polynomials. And I think we had an example of that on one of our worksheets where we had a change of direction at 0, where you had like an x squared where it was equal to 0 and so on. So we're going to use kind of the same basic principles and ideas throughout that we've done before, which is higher level polynomials. For example, if I look at this one, x cubed plus 27. It is two terms, x cubed and 27. Well, we haven't factored anything yet that's got a cube to it. So what we need to do is find out about special patterns. What I'm looking for are what are called cube roots. Cube root is kind of like a square root, but I'm asking what are three things that you multiply together that are the same. So what's the cube root of x cubed? What's the cube root of 27? 3. 3. Do you want to check that in your calculator real quick? Let me show you.
3 times 3 is 9.
In your calculator, there's a button that does cube roots. I believe if you hit math, and I think it's option 4. Option 4 is cube root. And if I type in 27, it gives me an answer. Okay? Now, what happens if I have to check like a fourth root or a fifth root? I need to be able to change that nth root value. You would type in math, option 5. See how it says x root? By doing that, you get a cursor to where you can put in whatever number you want, whether it's a 2, 3, 4, 5, 7, whatever. You can type things in like that. Is that okay? Okay. So that's where you get those two. Remember when we also did the y squared stuff to work with checking for square roots, perfect squares and things? Remember how we did x squared, or x divided, or x squared divided by, or I'm saying it backwards, 12 divided by x squared, and we would find that it was 2 root 3 in our table? We can do the exact same thing with cube roots, but using, instead of divided by x squared, we're divided by x cubed. Okay? Let me show you a quick example, because this will come up from time to time. Let's do 54. Everybody okay that 54 is 27 times 2? And we all know that the cube root of 27 is what? 3. So that means right now we should think that the cube root of 54 would be 3 cube root 2. Should be. Watch what happens. If I do 54 divided by x, do you guys know where the button is to get to your cube root? The caret? Above the division symbol? I had people ask me earlier, like, wait, where is that? And then you hit a 3. Now, if you go to your table function, you're still looking at that same possible stuff here. We're scrolling through looking for integer value. So it's 3 cube root 2. This is how you can simplify any, what we call nth roots. Whether it's a cube root, fourth root, whatever, you're just going to change your denominator to whatever the root is. Are we okay with that? Just a little thing that'll help because you'll be simplifying things through to try to find those things out. So what we get here is what we call a sum of cubes. And there's a special pattern that occurs with these things. We're going to have sum of cubes and a difference of cubes. I'm going to write out the formula, if you want to call it that, or the pattern, and then I'll walk you through how this works. If you have a cubed plus b cubed, basically, in this example, x is playing the role of a, and 3 is playing the role of b, because 3 cubed is 27. What happens is you get this special pattern. Whatever a plus b is, times first term squared, ab, and last term squared. And here's what happens with your signs. The second sign that you always put in will always be the opposite of what it starts as. So if this starts as a plus, the second sign will be minus, and the last sign always ends up as plus.
The last sign is always plus?
Always plus, for both sum and difference. Because then the difference, might as well write this up real quick. You can see the difference, you can see how they're very similar.
Is it the same thing as add?
Well, see how this one starts as plus?
Yeah.
This one's going to start as minus, and then what's the next one going to be? Yeah.
Didn't I have something like this happen on my homework?
What's that?
I thought I saw something like that.
You haven't had to do this yet. You haven't had to factor anything with a cube root yet.
Yeah, but I mean, like, we got, like, the answer.
Yes, you had to you foiled in, you wound up with a perfect or a difference of cubes or sum of cubes. Yes, that was already there, but we didn't talk about anything else. So, I'll write it out here too for you guys. Oops. And it really is a very simple pattern to work with.
So the last one is always plus?
Yes, the last one will always be plus. The first one's always whatever the sign is between the two. The second sign is just the opposite. Now, what you're going to want to be able to do is basically figure out which value plays the role of A, which value plays the role of B. So if I go back to my original problem here, I've got the x cubed plus 27. I have the x cubed plus 27. What's playing the role of A? What's playing the role of B? And then 3 equals B, because it's A cubed, B cubed. Okay? So it's just a matter of filling in the blanks. X plus 3, x cubed, 3x, and a 9. And then my signs are just minus, plus. That's it. Yes, ma'am?
Is it x cubed or x squared?
Thank you. I was saying 3 as I wrote it, and I did that by mistake. Thank you. The idea here is that you have to just be able to identify which parts are what, and go from there, and fill in the blanks. Okay? If I go to the other problem that we had there, the other one, it was, I forgot. It works. There we go. When I do the other one, what's the first rule of factoring, no matter what? GCF. What's the GCF of 16? Is it okay if I keep saying x? Yeah. By all means, because they use all the different letters, it's just kind of silly. 16x to the 5th minus 250x squared. What is the GCF? Maybe 2. Yeah. So if I factor that out, factor out my GCF, I have 2x squared I'm going to take out. And then I'm left with 18x cubed minus $1.25. Okay? Now, is 8 a perfect cube?
Yeah.
How can you check that? Now, here's what happens then. That means that your value of A, if you want to think of it this way, is 2x. The value of A in this case is just 2x. Most of you guys will forget that the 2 is there. Okay. The second part, what's the cube root of 125? 5. I would seriously suggest, until you get the hang of these things with with differences of cubes and, or not difference, sums and differences of cubes, I would write these 2 out a couple times just to get the hang of it. Okay. So now it's a matter of following the pattern. 2x squared is still here, so I bring it down again, and I follow the pattern. The difference of cubes was A minus B, so 2x minus 5. And then the second part was 2x squared plus, very good, 10x, and then it's plus 25. The reason I wrote that 2x quantity squared is because I have that 2x is following the rule of A. 2x quantity squared is 4x squared. Pattern-wise, Blanc, you got the pattern here. Remember, it's A cubed minus B cubed equals A minus B, A squared plus AB plus B squared. This case here, A is 2x, B is 5. And I take the coefficient of that first term because it's a perfect cube. I'm just filling in the blanks. Whenever I have a leading term coefficient, that's especially where I just have to pay a little bit closer attention to it. And we'll go from there. Quite honestly, this is really the only thing that's kind of new for what we're doing today. There's this special pattern. I will recommend whenever we see it, write it out a couple of times and you'll commit it to memory. It's not a difficult pattern to keep tabs on. It just looks good. Okay? I was going to say kind of cute, but I didn't want to do that. Show you nothing. We actually have done this problem. One of the suggestions, one of the things that I've always told you guys, whenever you have 4 terms, whether it was a quadratic, when we wind up with 4 terms quadratics, we always factored by grouping, because that's how we did, we called it split middle term. We broke it down into 4 parts, and we were able to group things out and do GCFs twice. It's exactly the same thing if you see upper degree polynomials. Whenever you have 4 terms, the first thing you do is see if there's a GCF, and if not, try to group them. You always want to make sure they're in descending order, though. The degrees go down. 3rd degree polynomial, there are 4 parts possible to it. Remember when we talked about that? We had 3rd degree, 2nd degree, 1st degree, constant. That's why there's 4 terms. If I group that, all I'm doing is throwing parentheses at the front, 2, parentheses at the back, 2, and getting GCFs. Getting GCFs, you guys are good at that. That's easy. Right? So, group them. Whenever you have a 3rd term that's negative, do that so it forces you to remember that there's a negative there to play around with. And now just ask about GCFs twice. What's the GCF of x cubed and 2x squared? X squared, very good. I'm then left with x minus 2. What's the GCF of the next part? Bless you. -9. And lo and behold, I'm left with x minus 2. Hey, are those two things in the parentheses the same? That's a good thing. Write it down. And you're left with x squared minus 9. Ooh, can I go further?
Yes.
What do you get?
X equals plus or minus 3x.
Oh, did you see an equal sign? If it's just factor, you don't see an equal sign. If you see an equal sign, then it'll say find the zeros. What way are your tails moving on this one? Well, what? You know, do your dance moves. Which way do the tails go? Which way are they? All right, dance moves. First term's positive, exponent's odd. Which way are the dance moves? Up, up, down, 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 up, or up, down? Down, up. They're down, up. So I know that these have to be down, up. Where are your zeros if it asks to do 4? 3, and then and a 2. So it'd have to do this. I don't know where the changes are, but I know it has to look like that. That's the idea of working with polynomials, is that you can continue to work on end behavior dance moves flowing through your zeros and change directions. Okay. Grouping, very, very common. You guys have all done that. It's not anything new. Okay. 81x to the 4th minus 16. It's two terms. There's subtraction between the two. That usually is a dead ringer to ask yourself the following question. Is 81x to the 4th a perfect square? Yeah. What's the square root of 81x to the 4th? 9x. Okay. Is 16 a perfect square? What is it? It's 4. Is that a subtraction sign between the two? That's just a difference of squares. It's a difference of squares. So you have 9x minus 4, or 9x squared minus 4, and 9x squared plus 4. Hey, look! I can go further, can't I?
No, you can't.
Hey, yeah! What's the square root of 9x squared? What's the square root of 4? Is that a subtraction sign? Yeah. I can go one step further. 3x plus 2, 3x minus 2. But can I do the same thing for the second term? Bless you. No, I can't because it's a plus sign. So it's asking me to factor this, which means all I have to do now is just rewrite it. And I'm done. There's nothing left for me to do. Correct, because then it's not a difference of squares then, it's a sum of squares. And there's no way for us to factor a sum of squares. Okay? Now, there is one other thing that we could possibly do here. Let's say it did say equal 0. At this point, if it said equal 0, you could still find your zeros. I have zeros at plus or minus 2/3. And then here I'd have x squared equals negative 4/9. And if I take the square root of that, what do you get? Plus or minus 2/3 I. Now notice, 4th degree polynomial has 4 possible zeros, both real and imaginary. We'll get to more and more of that as we go along. Sometimes it'll ask you for all possible solutions. Sometimes it'll ask you for all real solutions. Sometimes it might not even say equals. I'm just getting you guys to have seen the different things you can get. Okay. Second one, 4x to the 6th minus 20x to the 4th plus 24x squared. your first rule for all of these things, no matter what, is always to see if you have a GCF. If you have a GCF, take it out, okay? So when I do that, are you guys okay if I put that on a different sheet?
Wait, for the last one?
Yeah.
Isn't the 2 over 3i, isn't that imaginary, so would it not matter?
And good question. It'll say find all possible solutions, or it might say find all real solutions. So if it says all possible, you list out all 4. If it says all real, you just list the 2 that are real. Okay. More often than not, I ask for all possible, but it just depends on what's written. Yes, ma'am.
Don't grab 2/3
Okay, I am right now.
So
It's on count.
part of our like thing is finding like the zeros and stuff.
Yeah, I'll mix it all together, just like we did with factoring quadratics. When we factored quadratics, we factored some of them, we found zeros for some of them. The only time that you have to worry about finding a zero is if this say equals 0. If it doesn't, it just means factor.
Okay.
Okay, I'm just showing you that extra step because then we can do more examples.
Alright, I just had like,
A panic attack?
yeah, not good. I'm gonna crush
So,
pieces and
On this one here, we've already said that we have a GCF. What's the GCF? Good, it's 4x squared. So if the GCF is 4x squared, I'm then left with x to the 4th minus 5x squared. Now, looking at that internal quadratic, or 4th degree polynomial, notice how the exponents go from 4, half, or excuse me, 4, 2, and then nothing. That means I can factor it just like any other boring trinomial. Right. So what times what is 6? You add together to get -5. We get, so we have x squared minus 3 and x squared minus 2. Can I factor any of that further? No. But let's just say I wanted to set this one equal to 0 and then graph it. If it equals 0, Daniel, this is much easier than you're giving it credit for. How many terms do we have to set equal to 0 here? 3. Because there's 3 parts. So you do this. What's the 0 for the first one? 0. But will that one be replicated? Was that duplicated? It is. Because it's a squared term equaling 0, so you actually have 0 and 0 here. Not plus or minus 0, it's a duplicated 0 because it's an x squared, which means it changes direction at 0. Okay? The other 2 are easy. You get plus or minus root 3 and plus or minus root 2. Okay with that? Well, no, these are 0. What I'm saying here is that if I divide by 4, I get x squared equals 0. Well, what times what is the same number that gives you 0? 0 times 0. So I'm just saying there's 2 zeros here. Okay. So when I do this, which way are your tails going for this problem? Are we up, up, down, 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 up, or up, down?
Oh, wait, again.
Original problem. 4x to the 6. Is 6 even? Is 4 positive? Up, up and away. If I'm beautiful. Sorry. So I know my tails will be up, up. And I have zeros. This is actually kind of cool. I have positive or negative root 3, negative root 2, 0. So it's going to do this. Change direction. It's going to look like that. Why? Because tails are up, up. Tails are up, up, so it's going to go down, change direction, come up, change direction, touches, changes direction, goes down, and goes back up. It has to look like that. I don't know where those localized maximums and minimums are going to occur, but because of the way that the, since it's a 6th degree polynomial, I can have up to 6 zeros, and I can have up to 5 changes of direction. I know my tails are up, and I just follow it through. Yes, sir? The localized maximum minimums? It's very simple to do because all you do is press buttons and calculator. I'm not going to do it any other way. Okay? Because I can ask you for the localized maximum minimum between a certain range, and all you're doing is just looking for it within that parameter. It's really easy. It's just like 3 buttons. And you know how to do that with just find a maximum, find a minimum. It's the same thing. Okay? So don't worry. And I see Hannah's like ready to throw something in the back, and I'm trying to get him to calm down. You guys okay? I don't know. Breathe. Haley, are you okay?
Yeah, I'm okay.
All right.
Real life situations.
I don't know.
Everything, Artie, everything.
I don't know. Just in case you have to graph it.
That's how they make pencils.
Yes, it's how they make pencils. All right, solve this one. Excuse me. Yeah. This is how they model the prices for bread.
What?
Wow. So I was like,
So they clean
for
their
freshmen,
bread like
they were like, talking about like all the bread, and so I was like, I don't know what's bread for it. How do they pay for it? I was like, is this bread?
So, whenever you start with these things again, since you know they're going to have something that's going to be equal to 0, why not move it as you're writing the problem down? Okay. So as I'm writing this down, I'm going to put this in descending order. I'm going to get 2x to the 5th minus 14x cubed plus 24x is 0. Okay. Now, right away, I know what my tails are doing. I have a positive first term. I have a, what is it called? An exponent that is odd. So is it going to be up, up, down, 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 up, or up, down? Down, up. Very good. We know it's going to go down, up. So first rule of factoring is thing. Yes, very good. Thing. What that thing is called?
greatest common factor.
So you take out a 2x. X to the 4th. What's that, Lori? No, I heard you. I thought you had a question. That internal trinomial then, notice how it follows the patterns of regular boring quadratics.
Okay.
So what times what is 12? You add together to get -7. No, we won't have time for this week.
If you get the graph,
Guys, come on. From here, do I have to factor any further?
Yes.
Do I really though?
No.
At this point, this is when you can start to make the decision whether or not you want to graph, or not graph, if you want to continue to factor, or do you want to just start solving your zeros? At this point, I would just solve my zeros because I can. I have squared terms, I can work through them without too much of a hassle. So all I'm going to do is set all 3 of these terms equal to 0, and I get a 0 plus or minus 2 and plus or minus root 3. If I wanted to rough sketch this, -2, negative root 3, 0, root 3, and 2. Tails are going down, up, so it's going to go through, change, through, change, through, change. That's it. I'm not worrying about how fancy schmancy all those values are going to look. I don't know if the peaks and valleys are that close or whatever. I'm not sure, but it's going to look something like that because it has to because of the rules of the tails, the end behavior, if you want to call it that. All right. All of these follow the same patterns. There's really nothing crazy to this. All right. What's wrong with it? And people didn't know Morse code, so there you go. You would if you were dying.
You know what? It's my time to die. It's my time to die.
Last one, and I'll give you some props. When you guys grouped this one, so you have an x squared, 3x plus 7. Take out the, was that -4? 3x plus 7 gives you x squared minus 4. 3x plus 7. 0 is at plus minus 2 and -7/3. Yay! It isn't like any different than what we've done. It's just higher degree polynomials. You might have to do one extra difference of squares towards the end. That's about it.
I like this kind of stuff.
When we get into stuff over tomorrow and into Friday, we're going to be doing more of the, yes ma'am? Yes. Because it's duplicated here. Because when you have something that is just, it's x squared equals 0.
I guess it was
It's going to be, since there's no plus minus
know we
value
did
equals 0. That means it's 0 times 0.
You played
So there's two zeros.
I went out and played softball. Dude, my team.
Yes. It's or if it's a x plus 3, x plus 3, then it changes direction and they go. Because what you can do here is
No, we can play our own game.
Write up a thing
Oh, like, we had everyone do it. We had
writing up a 5-book lab.
Alex Wisdom, we had Keegan.
I have to finish this.
Shepard was doing surprising things. Eric Smith.
no, these are just zeros because these are plus minus.
Shepherd.
He was doing surprisingly well.
He's so dumb. Yeah, he's probably
He quit? Oh, he's back.
Why did
All right, that's an 82. Sorry, I thought I was made that work. I counted wrong.
I feel like everyone.
Okay. We'll roll through those for tomorrow, and then we'll go on from there. Hopefully, we'll be able to do some complete the squared or not complete synthetic division tomorrow.